beyond the observable universe could reveal the process of galaxy formation and evolution on scales, and in environments different from those we can observe. The interaction between these black holes and their surrounding dark matter halos, interstellar gas, and star systems could provide unique insights into the dynamics of galaxy formation in different cosmic epochs and environments. The existence of black holes with properties or behaviors not predicted by current theories could open the door to new physics. This could include black holes in higher dimensional space, as predicted by some theoretical models, or black holes with unusual charge or spin characteristics that challenge our understanding of astrophysical processes. These anomalies could hint at the existence of exotic particles, fields, or principles of physics that only manifest under the extreme conditions present at black hole event horizons. While black holes are well-established objects in cosmology, known for their extreme gravitational pull from which not even light can escape, the idea that they might serve as bridges or tunnels to distant parts of the universe or to other dimensions is grounded more in theoretical physics than in observational evidence. Yet, this notion captivates the imagination and invites exploration into the limits of our understanding of the universe. At the heart of this idea is the theoretical construct known as a wormhole. Wormholes, solutions to the equations of general relativity, are hypothetical tunnels through the fabric of space-time, connecting two distant points in the universe, or potentially linking different universes altogether. In some models, the entrance to a wormhole could resemble a black hole, possessing a horizon beyond which the laws of physics, as we know them, begin to break down. Theoretical physicists speculate that, if wormholes exist, they could in principle allow for instantaneous travel across cosmic distances, or serve as gateways between different universes in a multiverse framework. However, several formidable challenges stand in the way of this being more than theoretical speculation. For one, the stability of wormholes is a significant issue. Calculations suggest that they would collapse too quickly for anything to travel through unless they are kept open by a form of exotic matter with negative energy density, something that is yet to be discovered or understood. The very notion of traveling through a black hole to emerge in another part of the cosmos or a different dimension confronts us with the problem of singularity at a black hole's core. According to current theories, at its core lies a point of infinite density where the laws of physics no longer apply as we know them. How matter or information could pass through the singularity intact is a profound mystery, one that challenges our current understanding of physics. The early universe, a period just after the Big Bang, holds crucial clues about the cosmos that extend beyond the observable limits. This primordial epoch, encapsulated in the cosmic microwave background radiation, provides a snapshot of the universe that was only 380,000 years old. By studying the CMB, scientists gain insights into conditions that prevailed in the early universe, offering hints about the vast cosmos that lies beyond our current observational capabilities. One of the key clues from the early universe is the uniformity of the CMB across the sky. This surprising uniformity suggests that different regions of the universe, even those that are not causally connected, meaning light has not had time to travel between them since the Big Bang, have similar temperatures. This observation has led to the inflation theory, which posits that the universe underwent a rapid expansion shortly after its birth, smoothing out any initial irregularities. Inflation implies that the regions beyond our observable universe were once connected to our own and therefore might share some of its fundamental properties. This connection hints at a cosmos that is homogeneous on the largest scales, extending far beyond what we can see. The quantum fluctuations that occurred during inflation are another crucial clue. These tiny variations in density, magnified by the inflationary expansion, became the seeds for all future structure in the universe. Galaxies, clusters of galaxies, and the vast cosmic web. Observing these fluctuations in the CMB provides a direct link to the processes occurring in the very early universe, suggesting that similar structures could exist throughout the cosmos, even in parts we cannot observe. The distribution and nature of these fluctuations can inform models of cosmic inflation, offering insights into physics governing the universe at its most fundamental level. The early universe's clues about dark matter and dark energy, two of the most mysterious components of the cosmos, extend our understanding beyond the observable. The way galaxies and galaxy clusters formed and evolved under the influence of dark matter, observable in the CMB's slight anisotropies, implies that dark matter's presence and properties are consistent throughout the cosmos. Similarly, the accelerated expansion of the universe, attributed to dark energy, affects the fabric of the entire cosmos, suggesting that the dynamics of dark energy observed within our cosmic horizon apply universally. The study of primordial elements such as helium and lithium, formed during the first few minutes after the Big Bang in a process known as nucleosynthesis, offers additional clues. The relative abundances of these elements, consistent with predictions across observable regions, support the idea of a uniform set of physical laws and conditions extending throughout the universe, including beyond our observable limits. Lastly, gravitational waves, ripples in the fabric of space-time generated by violent cosmic events, or even the initial moments of the universe itself, carry information about the very early universe that could extend to the unobservable cosmos. Detecting these waves in the infant universe could unveil phenomena or structures in the cosmic landscape beyond our current reach. During the first fractions of a second after the Big Bang, the universe underwent a phase of rapid expansion known as cosmic inflation. This exponential growth stretched the fabric of space-time, smoothing out any initial irregularities and creating a remarkably homogeneous universe on large scales. This inflationary period is pivotal because it determined the large-scale structure of the entire cosmos, including regions far beyond our observable limits. It suggests that the vast expanse of the universe, even the parts we cannot see, shares a common origin and was subject to the same rapid expansion, laying down a uniform foundation across the cosmos. The quantum fluctuations that occurred during inflation also played a crucial role. These tiny variations in density were amplified by the inflationary expansion, becoming the seeds for all future cosmic structures, from galaxies to superclusters. The distribution and evolution of matter in the universe's distant regions likely trace back to these initial fluctuations, meaning the large-scale structure we observe in the cosmos has its roots in the quantum-scale physics of the universe's first moments. Additionally, the synthesis of primordial elements, hydrogen, helium, and traces of lithium and beryllium, occurred within minutes after the Big Bang during a period known as Big Bang nucleosynthesis. The relative abundances of these elements, determined by the conditions and processes in the universe's first moments, would be consistent throughout the cosmos, affecting the chemical composition of stars and galaxies in even the most distant regions. The imprint of these first moments is also potentially observable in the cosmic microwave background radiation, which permeates the entire universe. Let's take a trip back in time, starting with the Big Bang that made space and leading to the galaxies we see at night. We'll learn about how stars are born and die, what makes our solar system work, and even the chances of finding life somewhere else in space. Join us as we uncover the secrets of the universe, how it affects us here on Earth, and what might happen in the future. The Big Bang Theory is the leading explanation for the origin of our universe. Imagine the universe as an immensely dense and hot point, roughly the size of a grain of sand. This point contained all the energy and matter that would eventually form everything we see today. Around 13 billion years ago, this tiny speck began to expand rapidly, an event we now refer to as the Big Bang. This expansion wasn't just an explosion in space. Rather, it was the expansion of space itself. In those first moments, temperatures soared to unimaginable heights, and as the universe expanded, it cooled down. This cooling allowed quarks and electrons to form. When conditions became favorable, these quarks combined to create protons and neutrons, forming the building blocks of atoms. Over millions of years, clouds of hydrogen and helium, the simplest elements created during this period, began to coalesce under gravity's influence, leading to the formation of stars and galaxies. The light we see today from distant galaxies can be traced back to this primordial event, giving us a glimpse into the universe's early moments. The Big Bang Theory also accounts for the observed abundance of these light elements and the cosmic background radiation that fills the universe, an afterglow from that early moment. This radiation serves as a snapshot of the infant universe, revealing information about its composition, temperature, and expansion. In this way, the Big Bang Theory not only explains how the universe began, but it also opens a window into the fundamental processes that continue to shape it today. The theory of cosmic inflation emerged from the need to explain certain puzzling aspects of the universe's early development. Scientists recognize that the observable universe is remarkably uniform. This means that despite vast distances between galaxies, the cosmic microwave background radiation, a remnant from a hot, dense state shortly after the Big Bang, is evenly distributed. However, this uniformity raises a question. How could regions so far apart be so similar if they had never been in contact? To address this conundrum, cosmologists propose that an incredibly rapid expansion, or inflation, occurred just after the Big Bang. This expansion would have stretched those small, uniform regions across vast distances in a fraction of a second, smoothing out variations and creating the homogeneity we observe. Supporting evidence for inflation comes primarily from observations of the cosmic microwave background itself. Measurements from satellite missions, such as the Wilkinson Microwave Anisotropy Probe, have revealed slight temperature fluctuations in this radiation. These tiny deviations in temperature point to the quantum fluctuations in density that would have existed before inflation, which were then stretched to cosmic scales during that brief period of rapid expansion. Additionally, the large-scale structure of the universe, including how galaxies are distributed in clusters and voids, aligns well with predictions made by inflation theories. It suggests that these structures formed from the small, initial inhomogeneities forged during the inflationary epoch. Finally, studying gravitational waves. Ripples in space-time that are generally produced by immense cosmic events has provided another potential layer of evidence. If inflation generated gravitational waves as theorized, future observations could validate the inflationary model even further. Thus, the theory of cosmic inflation not only began as an elegant solution to a significant question, but it has also been supported by consistent observational results that fit within the framework of our understanding of the universe's evolution. The formation of the first atoms was a pivotal moment in the history of the universe, setting the stage for everything that would come after. After the Big Bang, the universe began as a hot, dense soup of particles, primarily composed of protons, neutrons, and electrons, all zipping around at incredible speeds. As the universe expanded, it started to cool down, and this cooling allowed these particles to combine and form the simplest type of atom, hydrogen. In this primordial environment, hydrogen atoms began to emerge as the first stable units of matter. These hydrogen atoms eventually clumped together under gravity, forming the first clouds of gas. As these clouds continued to gather mass, they sparked the birth of the very first stars. It's fascinating to note that these stars were mainly composed of hydrogen, and in their cores, through the process of nuclear fusion, they began to transform hydrogen into heavier elements like helium and beyond. This transition was crucial. The first stars acted as cosmic furnaces, forging new elements essential for the complexity of the universe we observe today. When these stars reached the end of their life cycles, they exploded in powerful supernovae, scattering these newly created elements throughout the universe. This widespread distribution enriched the interstellar medium, laying the groundwork for the formation of planets and, eventually, life. Thus, the formation of the first atoms was not merely the birth of matter, but the beginning of a chain reaction that would lead to the creation of stars, galaxies, and the vast structures we see today. It was an extraordinary leap from a hot, chaotic state to a structured universe, revealing the power of simple building blocks in shaping complex systems. Throughout this process, stellar winds and the gravitational influence of these young galaxies caused gas clouds to compress, triggering the birth of new stars. This cycle of star formation, aging, and death intricately shapes the galaxy's structures and sizes. Galaxies can be broadly categorized into several types based on their shapes and characteristics. The most common are spiral galaxies, identifiable by their swirling arms that extend from a central bulge. These arms often house star-forming regions filled with young, bright stars. In contrast, elliptical galaxies resemble elongated spheres, exhibiting a smooth, featureless appearance. They typically contain older, cooler stars and less interstellar gas, meaning lower rates of new star formation. Then, There are irregular galaxies, which defy any simple classification owing to their chaotic shapes. They often contain a mix of young and old stars and can result from gravitational interactions or collisions with other galaxies, leading to their unpredictable appearances. Finally, there are lenticular galaxies, which present characteristics of both spiral and elliptical galaxies. Similar to an elliptical structure, yet possessing a disk, they often feature a bulge in the center but lack pronounced spiral arms. Each galaxy type tells a story of the cosmos, revealing the complex interactions of gravity, light, and time that shape them. Their study not only enhances our understanding of the universe's history, but also provides insights into the ongoing processes that govern cosmic evolution. Dark matter is an elusive substance that makes up a significant portion of the universe's total mass, yet it does not emit or absorb light, making it invisible and detectable only through its gravitational effects. Think of it as an unseen framework that guides the formation and behavior of galaxies. Without dark matter, the universe, as we understand it, would look vastly different. As galaxies form, they gather mass from clouds of gas and dust. Gravity pulls this matter together. But for galaxies to develop their spiral shapes and maintain their structure, they require much more mass than what we can see. This is where dark matter becomes crucial. It exists as a vast halo surrounding galaxies and extending well beyond their visible edges. This halo contributes the gravitational pull necessary to hold galaxies together and to ensure they rotate at the speeds observed, preventing them from flying apart. When we observe clusters of galaxies, we notice that the visible mass does not account for the gravitational effects at play. The outer regions of galaxies are rotating faster than they should if only the visible matter were present. The additional gravitational pull supplied by dark matter accounts for this discrepancy, indicating that there is much more mass influencing these astronomical structures than we can detect with our instruments. Moreover, dark matter plays a vital role in the larger scale structure of the universe. It acts as a scaffold that influences the distribution of galaxies and clusters, shaping the cosmic web we see today. Areas of higher density, where dark matter collects, attract ordinary matter, leading to the formation of galaxies. Thus, without dark matter, galaxies wouldn't just be different. Many of them might not exist at all. Its presence is fundamental to understanding how galaxies evolve, interact, and remain stable through cosmic time. Supermassive black holes sit at the heart of most large galaxies, functioning as colossal gravitational anchors within their cosmic neighborhoods. These behemoths can contain the mass equivalent to millions or even billions of suns, and their presence plays a crucial role in the evolution of galaxies. Imagine a massive sphere of darkness, surrounded by swirling clouds of stars and gas. This black hole exerts an immense gravitational pull, which helps to regulate the motion of surrounding stars. Their influence stretches outwards, shaping the structure of the galaxy itself. As stars orbit around these black holes, they experience changes in speed and direction, contributing to the overall dynamic behavior of the galaxy. Furthermore, supermassive black holes are linked to the activity known as active galactic nuclei. When matter spirals into a black hole, it heats up and emits powerful streams of energy, making the galaxy's core shine exceptionally bright compared to the outer regions. This brilliance can be observed across vast distances in the universe, serving as a beacon that helps astronomers study the formation and growth of galaxies over billions of years. Another key aspect of supermassive black holes is their role in galaxy evolution. The energy released during the process of accretion, when material is drawn into the black hole, can affect gas dynamics in the galaxy. It might influence star formation rates, either by heating surrounding gas, preventing it from collapsing into new stars, or by generating powerful outflows that redistribute material throughout the galaxy. Thus, the interplay between supermassive black holes and their host galaxies is intricate, casting a long shadow over their developmental pathways. Understanding supermassive black holes sheds light on fundamental questions about the cosmos, such as how galaxies form and evolve over time. It reveals the interconnectedness of structures across the universe, making them a focal point of modern astrophysical research. These enigmatic giants not only govern the behavior of their galactic hosts, but also unlock many mysteries about the history and fate of the universe itself. Galactic collisions are not just spectacular cosmic events. They play a crucial role in shaping the universe's large-scale structure. When two galaxies come close enough, their gravitational forces interact, pulling at each other with tremendous strength. This interaction can lead to various outcomes, from minor distortions to full-blown mergers, where the two galaxies combine into a single larger entity. As galaxies collide, their stars rarely crash into one another due to the vast distances between them. However, the gas and dust within these galaxies can collide, triggering a burst of star formation. This is akin to shaking a box full of marbles. The movement results in new clusters forming in unexpected places. As new stars ignite in these star-forming regions, they emit light that can illuminate the surrounding interstellar environment, influencing the formation of new structures. When they merge, they form heavier elements while releasing enormous amounts of energy in the process. To picture this, think of it as a series of delicate dances between particles in the heart of a star. Hydrogen nuclei come together to create helium, the second lightest element. This fusion of hydrogen into helium is the primary reaction in stars like our Sun, providing the energy that radiates outward and supports the star against gravitational collapse. The process doesn't stop there. As a star ages and exhausts its hydrogen, it fuses helium into heavier elements like carbon and oxygen. Eventually, even heavier nuclei can be created during the later stages of a star's life cycle, producing elements like neon, magnesium, and iron. During the life and subsequent death of these stars, the newly formed elements are scattered across the universe, enriching the interstellar medium. This cycle of fusion and explosion not only powers the stars, but also contributes to the creation of the diverse array of elements found on planets and in living things. Ultimately, fusion is not just a source of energy. It's the fundamental process that shapes the cosmos and provides the building blocks for everything we know. The life cycle of a star like our Sun is a fascinating journey that spans billions of years, beginning with its birth in a massive cloud of gas and dust. This cloud, composed primarily of hydrogen, begins to collapse under its own gravity. As the material clumps together, it heats up and forms a protostar, a dense ball at the core surrounded by a disk of gas and dust. Over time, this core continues to accumulate mass and temperature, eventually reaching conditions that ignite nuclear fusion. When fusion starts, hydrogen atoms combine to form helium, releasing tremendous energy in the process. This marks the birth of a main sequence star, a stable phase where the Sun will spend the majority of its life, approximately 10 billion years. During this time, the energy produced in its core counteracts the force of gravity, allowing the star to maintain a stable size and temperature. Our Sun, shining brightly and consistently, is currently in this main sequence stage. As the hydrogen fuel begins to deplete, the balance within the star starts to shift. The core contracts, causing it to heat up, while the outer layers expand and cool, transforming the Sun into a red giant. This phase initiates a new round of fusion. At this point, helium begins to fuse into heavier elements. The outer atmosphere of the Sun swells and could eventually engulf nearby planets. As the Sun exhausts its helium fuel, it will undergo further phases of instability. Ultimately, it will shed its outer layers, creating a beautiful shell of gas known as a planetary nebula. What remains at the core is a hot, dense remnant called a white dwarf, which no longer undergoes fusion reactions. This white dwarf will gradually cool and fade over billions of years. In the end, the Sun's journey showcases a life cycle of stellar evolution, marked by distinct stages over immense time scales. From a glowing ball of gas to a luminous celestial specter, the transformation is a reminder of the dynamic processes governing our universe. Massive stars have a dramatic life cycle that culminates in an explosive finale. Throughout their existence, they undergo a series of nuclear fusion processes, fusing lighter elements into heavier ones, sustaining their energy output and balance against gravitational collapse. As a massive star exhausts its nuclear fuel, it transitions through various stages, creating elements like carbon, oxygen, and even iron in its core. Eventually, when iron begins to accumulate, a critical change occurs. Iron does not release energy when it fuses. Instead, it absorbs it. This marks the point where the star can no longer support itself against the immense gravitational forces pulling inward. With no energy-producing reactions to counteract this force, the core succumbs to gravity, collapsing rapidly while the outer layers of the star remain intact for a brief moment. In this cataclysmic end, the core's collapse leads to an extraordinary rebound effect. It's akin to a bounce back from a deep dive. The outer layers, unable to maintain their support, implode towards the core and are then violently expelled outward. This colossal explosion is what we know as a supernova. In that moment, a supernova releases a brilliant burst of light and energy, outshining entire galaxies for a period. It disperses the star's materials into space, enriching the interstellar medium with the elements forged during its lifetime. What follows is equally fascinating. The remnants of the core, depending on its mass, can become either a neutron star or, if particularly massive, collapse into a black hole. The death of a massive star is a grand recycling event, seeding the cosmos with the building blocks for future stars and planets, driving the very evolution of the universe itself. When massive stars reach the end of their life cycles, they undergo a dramatic transformation that can lead to the birth of either neutron stars or black holes. This transformation begins once a massive star has exhausted the nuclear fuel in its core. As the core collapses under its own gravity, it becomes increasingly compact. If the remaining mass of the core is not too extreme, it compresses to the point where protons and electrons combine to form neutrons, resulting in a neutron star. Imagine an object with the mass of a sun, but shrunk down to the size of a city. The density here is astronomical, as a small spoonful of neutron star material would weigh about the same as an entire mountain on Earth. This incredibly dense condition creates a powerful gravitational field. Neutron stars often spin rapidly and emit beams of radiation, leading to the mesmerizing phenomenon known as pulsars. On the other hand, if the core's mass exceeds a certain limit, often described as a threshold, that is more than just a few times the mass of the Sun, the gravitational collapse continues unabated. In this case, no known forces can counteract the pull of gravity, and the star collapses beyond the neutron star stage into a black hole. Visualize it as a region where gravity is so strong that nothing, not even light, can escape it. The boundary surrounding this region is called the event horizon, where all paths lead inward. The explosive deaths of these massive stars, particularly through a supernova, often scatter their outer layers across space, leaving behind these remnants, either neutron stars or black holes, which profoundly influence their surroundings. The evolution of these entities illuminates the intricate dance of nature's forces at work in the universe, revealing how the end of one existence can seed the beginnings of others. The formation of our solar system is a fascinating story that begins with a massive cloud of gas and dust known as a solar nebula. Imagine a colossal nebula composed of elements that were forged in previous generations of stars. This cloud became unstable, possibly due to shock waves from nearby supernova explosions. Slowly, it began to contract under its own gravity, causing the material at its center to accumulate and heat up, forming what we recognize as the Sun. As the Sun ignited, it released energy that pushed much of the remaining gas outward, creating a spinning disk of material surrounding it. Within this spinning disk, particles collided and stuck together, gradually forming larger and larger clumps, a process known as accretion. These clumps eventually became the planets, moons, comets, and asteroids we see today. The inner section of the disk, where it's hotter, allowed the formation of rocky planets like Earth and Mars, while the outer regions, being cooler, birthed gas giants like Jupiter and Saturn. Current theories about this process are grounded in extensive observations and simulations. One central idea is called the solar nebula theory, which details how gravity and the conservation of angular momentum led to the systematic formation of our solar system's various bodies. This theory explains not only the arrangement of planets, but also their compositions and orbits. Another theory gaining traction is the concept of the Nice model, named after the city in France where key research took place. This theory suggests that the early solar system underwent significant rearrangement. Specifically, after the planets formed, gravitational interactions between them, particularly the large gas giants, led to dramatic changes in their orbits. This could explain the unusual orbits of some distant objects, known as trans-Neptunian objects, and the steep incline of the solar system's outer region. Overall, while we have a solid understanding of the general processes involved in the formation of our solar system, researchers continue to study its intricate details, piecing together the cosmic puzzle that created our home. Amidst the vastness of the universe, Earth stands out in our solar system as a uniquely hospitable planet for life, and several key factors contribute to this distinction. First and foremost is its position in what scientists refer to as the habitable zone, an area around the sun where conditions are just right for liquid water to exist. Water is essential for life as we know it, acting as a solvent for biochemical reactions and playing a crucial role in regulating temperatures. Furthermore, Earth's atmosphere is a critical component of its ability to support life. It is composed mostly of nitrogen and oxygen, creating a stable environment that not only protects living organisms from harmful radiation, but also helps maintain a comfortable temperature range. This protective layer shields the planet from the sun's intense rays and allows for weather patterns that distribute heat and moisture. Another important characteristic is Earth's geological activity. The presence of tectonic plates contributes to a dynamic environment that recycles nutrients and shapes diverse habitats. This geological process not only creates varying landscapes, from mountains to valleys, but also plays a pivotal role in the carbon cycle, which helps regulate the planet's climate over long periods. Additionally, Earth's magnetic field serves as a shield against solar winds, which are streams of charged particles emitted by the sun. This magnetic barrier protects the atmosphere from being stripped away, ensuring that vital gases remain and are not lost to space. Life on Earth has also benefited from its relatively stable climate and the planet's abundance of diverse ecosystems. From lush rainforests to arid deserts, these varying environments provide numerous niches where life can thrive. In sum, Earth's ideal location, protective atmosphere, geological activity, strong magnetic field, and diverse ecosystems all work in unison to create a planet that is uniquely suited for the complex and varied forms of life that call it home. Scientists explore the possibility of life on Mars and other planets through a multifaceted approach that combines technological ingenuity and methodical exploration. They begin by focusing on environments where life as we know it could exist, specifically looking for the presence of water, as it is essential for life. On Mars, missions have detected evidence of past water flows, such as riverbeds and minerals that form in water, suggesting that the planet once had favorable conditions for life. Robotic missions play a pivotal role in this exploration. Rovers, equipped with a variety of scientific instruments, traverse the surface of planets, analyzing soil and rock samples to identify organic compounds, the basic building blocks of life. These rovers are capable of conducting experiments in situ, meaning they analyze their surroundings without needing to return samples to Earth. This allows scientists to gather immediate data about the planet's chemistry and potential biological activity. Moreover, telescopes and space probes extend our reach to distant worlds. They analyze atmospheres and surface conditions by detecting gas signatures, such as methane, which may indicate biological processes. For instance, the presence of specific gas combinations could hint at the potential for life, requiring further investigation. Laboratory simulations also provide critical insight. Researchers recreate planetary environments on Earth to study how life might adapt or survive under extreme conditions, from the frigid temperatures of outer planets to the high radiation levels found on Mars. These experiments help scientists understand the limits of life and how it may exist under conditions very different from those on Earth. Collaborative international efforts enhance these endeavors. Space agencies share findings, technology, and expertise, fueling a collective understanding of where to look for life and how to interpret the data gathered. By piecing together geological history, atmospheric analysis, and potential biosignatures, scientists continue to unravel the mysteries of life beyond our planet, always searching for the tantalizing possibility that we are not alone in the cosmos. The outer planets, often referred to as gas giants, hold numerous mysteries and captivating traits that intrigue scientists and space enthusiasts alike. Unlike the rocky inner planets, these massive worlds are composed mainly of gases and possess different characteristics that set them apart. Jupiter, the largest of the outer planets, boasts a swirling atmosphere filled with storms, including the Great Red Spot, a gigantic storm larger than Earth that has raged for centuries. Its vast magnetic field and dozens of moons, including volcanic Io and icy Europa, suggest a dynamic system rich with geological activity and potential for life in the subsurface ocean believed to exist beneath Europa's icy crust. Saturn is renowned for its stunning rings, made mostly of ice particles and rocky debris. These rings, while beautiful, raise questions about their formation and lifespan. Saturn's numerous moons, such as Titan, capture attention as well. Titan features a thick atmosphere and lakes of liquid methane, offering a glimpse into an alien environment that is intriguingly similar yet starkly different from Earth. Uranus presents a unique tilt, rotating on its side relative to its orbit, creating extreme seasonal variations. Its deep blue color is due to the presence of methane in the atmosphere, which absorbs red light. The planet and its moons, like Miranda, with its strange geological features, remain less understood and suggest a violent past, possibly involving collisions with other celestial bodies. Neptune, the farthest from the Sun, showcases some of the strongest winds in the solar system, reaching speeds that defy forecasts based on its distance from the Sun. Its vivid blue hue, also influenced by methane, hints at complex atmospheric processes, while its dynamic weather patterns and dark storms present opportunities for further research. Together, the mysteries of these outer planets invite ongoing exploration. They challenge our understanding of planet formation and evolution, pushing the boundaries of our knowledge about the solar system and the potential for diverse environments throughout the universe. Each of these planets, with its unique characteristics and enigmatic phenomena, contributes to an intricate picture of our cosmic neighborhood, urging scientists to unravel the secrets hidden within their thick atmospheres and icy moons. After the Big Bang, the universe began to expand, but it was initially influenced by gravity, which tended to slow this expansion. Over time, as galaxies moved apart, something unusual happened. Around 5 billion years ago, the rate of expansion began to rise instead of slowing down. This is where dark energy enters the picture. It works against gravity, overpowering it to send galaxies racing further apart at an accelerating rate. What dark energy exactly is remains uncertain, but it is thought to have a uniform presence throughout space. Unlike matter, which can clump together under the influence of gravity, dark energy remains evenly distributed, leading to a repulsive effect that pushes galaxies away from each other. Scientists suspect that it could be linked to the energy of empty space itself, a concept known as the cosmological constant, or might represent a dynamic field affecting the universe differently over time. As researchers continue to study this enigmatic force, it raises profound questions about the ultimate fate of the universe. Will galaxies drift so far apart that the night sky becomes dark and silent? The answers may redefine our understanding of space, time, and the very nature of reality itself. Scientists explore the possibility of other dimensions beyond our observable universe by delving into the fascinating realms of theoretical physics and advanced mathematics. Their quest often begins with the fundamental principles of our universe, specifically those defined by theories such as string theory and quantum mechanics. String theory posits that the basic building blocks of reality are not point-like particles, but rather tiny vibrating strings. These strings can exist in multiple dimensions beyond the familiar three of space and one of time. By employing mathematical frameworks, physicists theorize that additional dimensions might be compactified, meaning they could be incredibly small and tightly curled up, making them difficult to detect directly. Techniques like studying particle collisions in high-energy environments, such as those found in particle accelerators, help probe the energy levels where the effects of these extra dimensions might become evident. Furthermore, scientists investigate the cosmic background radiation, the afterglow of the Big Bang, looking for anomalies that could hint at dimensions beyond our observable universe. The idea is that interactions in these additional dimensions could manifest as slight discrepancies in the radiation's uniformity. Advanced astronomical observations also play a crucial role, particularly in studying cosmic structures and gravitational phenomena. The behavior of galaxies and the distribution of dark matter provide clues that could indicate the influence of hidden dimensions. Ultimately, while these concepts remain highly speculative, the constant interplay of theory, experimentation, and observation provides a means for scientists to inch closer to understanding the possibility of other dimensions and how they might shape our reality. The concept of wormholes and the potential for time travel emerged from the theories of relativity proposed by Albert Einstein. Einstein introduced the notion that space and time are intertwined into a single entity called space-time. They function as bridges, connecting separate points in space-time. Imagine being able to travel from Earth to a distant star system, not by moving through the vast emptiness in between, but instead by hopping through a tunnel that links them. These hypothetical structures, although mathematically possible, have yet to be observed in nature. Their existence relies on various exotic conditions, including the presence of negative energy, something we have yet to find in a stable, usable form. When considering time travel, the situation becomes even more complex. Einstein's equations allow for scenarios where time can be manipulated under certain conditions. For example, if one could travel at speeds approaching that of light, or even create a rotating black hole, one might theoretically experience time differently compared to a stationary observer. Such effects, known as time dilation, have already been observed in experiments with high-speed particles and precise clocks on airplanes. However, these theoretical avenues bear numerous complications. For instance, creating a stable wormhole may require technologies and materials beyond our current capabilities, as well as a profound understanding of quantum mechanics, which emphasizes the inherently unpredictable nature of the smallest constituents of matter. While intriguing ideas flourish around wormholes and time travel, the scientific community remains cautious. Current evidence leans on the foundation laid by Einstein's theories. Yet tangible proof is elusive, captured only within the realms of theoretical physics. As our understanding of the universe expands, the quest to validate these extraordinary phenomena persists, inviting both scientific inquiry and imagination. Detecting black holes is a fascinating challenge for scientists because they do not emit light. Instead, astronomers rely on indirect evidence to identify their presence. One of the main methods involves observing the effects of a black hole's gravitational force on nearby stars and gas. When a star orbits around an invisible object, that object's mass can be inferred by how fast the star moves and its path through space. This dance of celestial bodies can reveal the presence of a black hole, even when it's completely shrouded in darkness. Another crucial method utilizes the detection of X-rays. If a black hole is actively consuming material from a companion star, the intense gravitational forces compress and heat that material, causing it to emit X-rays. Telescopes that can observe these high-energy emissions, like the Chandra X-ray Observatory, have provided compelling evidence for numerous black holes lurking in our universe. Recent findings have advanced our understanding of black holes significantly. For instance, scientists at the Event Horizon Telescope collaboration managed to capture the first image of a black hole in the galaxy M87. This monumental achievement provided a visual confirmation of their existence and offered insights into their structure, showing a dark shadow surrounded by a bright ring of light composed of superheated gas. Additionally, gravitational waves, ripples in space-time caused by massive cosmic events like black hole collisions, have opened up a new frontier in astronomy, gracefully detected by the LIGO and Virgo observatories. These waves provide a fresh way to study aspects of black holes, including their masses and spins, as well as details about how often they merge. The latest research is not just about confirming their existence, but understanding their dynamic nature. Observations suggest that black holes can grow rapidly by devouring matter or merging with other black holes. This growth can influence the formation and evolution of galaxies, making black holes key players in the cosmic landscape. Their behavior, previously thought to be static, is now understood to be much more interconnected with the surrounding galaxy, propelling fascinating discussions about the role of these enigmatic giants in the universe. Quasars are incredibly luminous objects powered by supermassive black holes at the centers of distant galaxies. When matter spirals into these black holes, it heats up dramatically, emitting immense amounts of energy that can outshine entire galaxies. Imagine a single beacon of light that casts a glow across billions of light years, outshining all the stars in its host galaxy. These fascinating entities are key to understanding the early universe for several reasons. Quasars formed when the universe was still quite young, often just a few billion years after the Big Bang. Their brightness allows astronomers to study them even from vast distances, providing a glimpse into the conditions that existed during the universe's formative years. By observing quasars, scientists can gather crucial insights about the growth of black holes, the formation of galaxies, and the distribution of matter in the early cosmos. They serve as cosmic time capsules, revealing not just their own properties, but also how the universe evolved over time. Studying quasars helps researchers understand large-scale structures, the rate of star formation, and even the influence of dark matter, highlighting their significance in piecing together the narrative of our universe's ancient history. After the Big Bang, the universe began to expand, but it was initially influenced by gravity, which tended to slow this expansion. Over time, as galaxies moved apart, something unusual happened. Around 5 billion years ago, the rate of expansion began to rise instead of slowing down. This is where dark energy enters the picture. It works against gravity, overpowering it to send galaxies racing further apart at an accelerating rate. What dark energy exactly is remains uncertain, but it is thought to have a uniform presence throughout space. Unlike matter, which can clump together under the influence of gravity, dark energy remains evenly distributed, leading to a repulsive effect that pushes galaxies away from each other. Scientists suspect that it could be linked to the energy of empty space itself, a concept known as the cosmological constant, or might represent a dynamic field affecting the universe differently over time. As researchers continue to study this enigmatic force, it raises profound questions about the ultimate fate of the universe. Will galaxies drift so far apart that the night sky becomes dark and silent? The answers may redefine our understanding of space, time, and the very nature of reality itself. Scientists explore the possibility of other dimensions beyond our observable universe by delving into the fascinating realms of theoretical physics and advanced mathematics. Their quest often begins with the fundamental principles of our universe, specifically those defined by theories such as string theory and quantum mechanics. String theory posits that the basic building blocks of reality are not point-like particles, but rather tiny vibrating strings. These strings can exist in multiple dimensions beyond the familiar three of space and one of time. By employing mathematical frameworks, physicists theorize that additional dimensions might be compactified, meaning they could be incredibly small and tightly curled up, making them difficult to detect directly. Techniques like studying particle collisions in high-energy environments, such as those found in particle accelerators, help probe the energy levels where the effects of these extra dimensions might become evident. Furthermore, scientists investigate the cosmic background radiation, the afterglow of the Big Bang, looking for anomalies that could hint at dimensions beyond our observable universe. The idea is that interactions in these additional dimensions could manifest as slight discrepancies in the radiation's uniformity. Advanced astronomical observations also play a crucial role, particularly in studying cosmic structures and gravitational phenomena. The behavior of galaxies and the distribution of dark matter provide clues that could indicate the influence of hidden dimensions. Ultimately, while these concepts remain highly speculative, the constant interplay of theory, experimentation, and observation provides a means for scientists to inch closer to understanding the possibility of other dimensions and how they might shape our reality. The concept of wormholes and the potential for time travel emerged from the theories of relativity proposed by Albert Einstein. Einstein introduced the notion that space and time are intertwined into a single entity called space-time. They function as bridges, connecting separate points in space-time. Imagine being able to travel from Earth to a distant star system, not by moving through the vast emptiness in between, but instead by hopping through a tunnel that links them. These hypothetical structures, although mathematically possible, have yet to be observed in nature. Their existence relies on various exotic conditions, including the presence of negative energy, something we have yet to find in a stable, usable form. When considering time travel, the situation becomes even more complex. Einstein's equations allow for scenarios where time can be manipulated under certain conditions. For example, if one could travel at speeds approaching that of light, or even create a rotating black hole, one might theoretically experience time differently compared to a stationary observer. Such effects, known as time dilation, have already been observed in experiments with high-speed particles and precise clocks on airplanes. However, these theoretical avenues bear numerous complications. For instance, creating a stable wormhole may require technologies and materials beyond our current capabilities, as well as a profound understanding of quantum mechanics, which emphasizes the inherently unpredictable nature of the smallest constituents of matter. While intriguing ideas flourish around wormholes and time travel, the scientific community remains cautious. Current evidence leans on the foundation laid by Einstein's theories, yet tangible proof is elusive, captured only within the realms of theoretical physics. As our understanding of the universe expands, the quest to validate these extraordinary phenomena persists, inviting both scientific inquiry and imagination. Detecting black holes is a fascinating challenge for scientists because they do not emit light. Instead, astronomers rely on indirect evidence to identify their presence. One of the main methods involves observing the effects of a black hole's gravitational force on nearby stars and gas. When a star orbits around an invisible object, that object's mass can be inferred by how fast the star moves in its path through space. This dance of celestial bodies can reveal the presence of a black hole, even when it's completely shrouded in darkness. Another crucial method utilizes the detection of X-rays. If a black hole is actively consuming material from a companion star, the intense gravitational forces compress and heat that material, causing it to emit X-rays. Telescopes that can observe these high-energy emissions, like the Chandra X-ray Observatory, have provided compelling evidence for numerous black holes lurking in our universe. Recent findings have advanced our understanding of black holes significantly. For instance, scientists at the Event Horizon Telescope collaboration managed to capture the first image of a black hole in the galaxy M87. This monumental achievement provided a visual confirmation of their existence and offered insights into their structure, showing a dark shadow surrounded by a bright ring of light composed of superheated gas. Additionally, gravitational waves, ripples in space-time caused by massive cosmic events like black hole collisions, have opened up a new frontier in astronomy, gracefully detected by the LIGO and Virgo observatories. These waves provide a fresh way to study aspects of black holes, including their masses and spins, as well as details about how often they merge. The latest research is not just about confirming their existence, but understanding their dynamic nature. Observations suggest that black holes can grow rapidly by devouring matter or merging with other black holes. This growth can influence the formation and evolution of galaxies, making black holes key players in the cosmic landscape. Their behavior, previously thought to be static, is now understood to be much more interconnected with the surrounding galaxy, propelling fascinating discussions about the role of these enigmatic giants in the universe's history. Quasars are incredibly luminous objects powered by supermassive black holes at the centers of distant galaxies. When matter spirals into these black holes, it heats up dramatically, emitting immense amounts of energy that can outshine entire galaxies. Imagine a single beacon of light that casts a glow across billions of light years, outshining all the stars in its host galaxy. These fascinating entities are key to understanding the early universe for several reasons. Quasars formed when the universe was still quite young, often just a few billion years after the Big Bang. Their brightness allows astronomers to study them even from vast distances, providing a glimpse into the conditions that existed during the universe's formative years.